Bon, écoutez, on va démarrer. Bonjour à tous. Good afternoon. It is my pleasure to welcome today Christophe Laux. Christophe Laux, who comes as a neighbor, because you are not far from here. Huh? You come from Centrale Supélec. So Christophe Laux is a graduate from Ecole Centrale de Paris. It was in 1988. It was still Ecole Centrale at the time. Today it is Centrale Supélec.
Mm-hmm. For
now.
Then,
For now. For now, yes, for now. Ça sera effacé. For now. And after that, you made a PhD at Stanford University. You stayed there after your PhD for 15 years, I guess, at Stanford University.
Including
research,
the PhD.
Including the PhD, okay. And then you came back to France at Centrale Supélec, laboratoire EM2C, which is the name of Energetic Macroscopic and Molecular Combustion,
Yes.
Where you lead the non-equilibrium plasma group. The name plasma appears somewhere in your title, of course. You are a fellow of the American Institute of Aeronautics and Astronautics, and in 2020 you received an ERC Advanced Grant called Green Blue Program to experimentally and numerically test new methods using nanosecond plasmas to promote the combustion of hydrogen or sustainable fuels with a drastic reduction of NOx emissions. So in the context of where there is an urgent need for greener aviation, it seemed to us interesting, but important, urgent to listen to you, dear Christophe. So please tell us about NOx reduction using plasmas.
Thank you, Riyad, and thank you very much for the invitation. Thank you also to all of you for being here today. And I'm very happy to talk about this topic that's very important to me, which is basically the reduction of greenhouse gases and atmospheric pollutants in aeronautical engines. But I should emphasize that this can be applied also to other types of engines. That's basically the topic I pitched for the ERC, and because it's better to be focused on something. So I worked indeed at EM2C, which is a laboratory with three components: a combustion component, a heat transfer component, and the plasma group, which I started in 2002 with David, who was my first PhD student at the time. He came from Stanford at the time with me when I came back. So, and also it's une unité propre of CNRS. Okay, so what we do in the plasma group, we do basically things that go from physics to applications, and so the applications are related to topics in energy, especially plasma-assisted combustion, but also the environment, CO2 conversion, clean hydrogen production, and air treatment. And we also have a lot of interest in space applications, in particular CubeSats, and a lot of work on atmospheric reentry. We have a Space Act agreement with NASA at the moment, and other projects with the Australia and Australian labs and Japanese labs. And so we do experiments that are based on these types of facilities using radio frequency plasmas, microwave plasmas, but also nanosecond plasmas, and I will talk about those later. We develop diagnostics. Typical diagnostics are to measure gas temperatures and species densities. And we do modeling and simulation. So the types of models we develop are collisional radiative models and kinetic models for a variety of gases, radiation models, and spectroscopy and hydrodynamic models. And we collaborate also with the people in the combustion group who do numerical simulations. Also, what we've done over the years is have spin-offs, and so there are 4 spin-offs today of the plasma group. 2 of them, the first 2, SpectralFit and Radis, are software to do spectroscopy, So for instance, spectral fit does spec air, which is for air species or species containing carbon, hydrogen, nitrogen, and oxygen. Radis is for all the Hytron species. And then two companies, Arity Technologies is based in San Francisco, and it does pulsars and a variety of applications. And finally, Spark Cleantech, the latest, is based here, and it produces clean hydrogen using methane pyrolysis. And here are all the fun people in the group. And I should say that we have two students that we co-advise who are currently at ONERA, who are at the bottom. And on the right, Erwan and Arthur are previous students who just came back to lead some spin-offs. And I should say that Arthur is leading a new spin-off on crystallization using plasmas. So let me go back to the topic of energy applications and in relation to the environment. Basically, aviation is responsible for 2% of CO2 emissions. 2%, it's about 1 billion tons of CO2 per year. It's as much as if everyone becomes a vegetarian, if you can save this CO2. So it has a lot of impact. So we know about this CO2 problem. However, there is more to the aviation problems. There is all this bad stuff here that's done by. My pointer doesn't work anymore. Here, do you see it? Yeah, all this bad stuff, and in particular nitrogen oxides, which are bad for the health. For now it seems okay. Bad for the health. NOx can attack the ozone layer in altitude. They can also produce extra ozone. NOx can produce extra ozone on the ground around airports, and that's not good for your respiratory system. And then you have also other bad stuff, such as sulfur dioxide, carbon monoxide, hydrocarbons unburned, and soot and particulates. So the CO2 problem is something that people are very well aware of, and Europe wants to reduce CO2 by 75% by 2050. But something that people know less is that Europe also wants to reduce NOx by 90%. Okay, how to reduce CO2? I think you heard that over and over on the news. Basically, people have two approaches. One is to use sustainable aviation fuel, which is fuel from halophytes, which are plants growing in salt water, so they don't detract from plants for food or land use for food, cooking oil, waste, and so on. And this is, of course, makes CO2 neutral combustion, because when the flame burns, it emits the CO2 that it used when the plant grew. The second approach is hydrogen, and you heard about what Airbus wants to do, the zero-emission hydrogen aircraft, which, of course, is CO2-free in terms of emission. Okay, so what's how much H2 and SAF does industry plan to use? This is the graph showing what the emissions of aviation, CO2 emissions in the EU until 2050. And you see that by 2050, more than 75% of the fuel will be H2 or SAF. And there will still be, interestingly, the project to keep some 17% of hydrogen and of kerosene, sorry. And with this strategy, they hope to reach zero emissions by 2050. Okay, so okay for CO2, that's done, assuming that we can make the hydrogen airplane and the SAF. But what about other pollutants? NOx, SOx, and burned hydrocarbons and soot. And people don't talk about them much, except the very respected scientific journal called the Wall Street Journal, that you may know of. And they wrote in 2021, well, I let you read it. Okay, hydrogen is not so cool because it makes a lot of NOx. And NOx is also, by the way, a greenhouse gas in addition to all the problems I mentioned earlier. And so this reinforces the idea of reducing NOx. Okay, how do they produce NOx? Via two reactions called the Zeldovich reactions, mostly. There are other processes, but this is the main one. And these reactions become more and more important at higher temperatures. And so how to reduce NOx? Well, you can reduce NOx by simply lowering the flame temperature. And this can be done by using what's called a lean fuel-air mixture. That is a mixture where the ratio of fuel is relative to the oxidant is less than what you would have under stoichiometric conditions. And so they define the fuel equivalence ratio. When it's less than 1, we talk about a lean mixture, lean flame. When it's more than 1, when there is an excess of fuel relative to the oxidant, you talk about a rich mixture. And so, well, these are curves of NOx emissions for typical aircraft engines on the left. So you have the NOx emissions as a function of the flame temperature here. And, well, what you see is that, well, NOx emissions increase quite fast with the temperature. Typically, if you can lower the flame temperature by 100 Kelvin, you can gain roughly 1 order of magnitude in NOx emissions. So you really want to lower the flame temperature. And how to do this? On the right, you have the flame temperature as a function of the fuel equivalence ratio. And you see that you have stoichiometric is almost at the center. So to reduce the flame temperature, you can either go rich, excess fuel, or lean. And, well, basically, you should choose the lean side, because on the lean side, not only you reduce flame temperature, but also because you don't have an excess of fuel, you burn all the fuel, so no unburned hydrocarbons and no soot. So this is what people are considering in industry. Go lean, burn lean. So that's great for aircraft engines. What about hydrogen? This graph was sent to me by Safran Aircraft Engines, and they made a calculation where they showed that the NOx emissions of hydrogen relative to those of kerosene. And basically, if you're at a fuel equivalence ratio of 0.8, hydrogen flames make 80% more, 70% more NOx than kerosene, which is a little known fact. People think hydrogen is clean. No, it burns at higher temperatures than kerosene, and so the higher the temperature, the more NOx, because you have, which is made from N2 and O2. Okay, and if you want to go below the level of kerosene, you need to go really low in fuel equivalence ratio. You need to go below 0.7. So again, even for hydrogen flames, you need to burn lean. And that's great. However, there is a problem. Lean flames tend to be very unstable to the point that they can even extinguish if they are too lean, or burn badly, and so they cannot produce much power. So the solution is to use, one potential solution is to use plasmas to stabilize the lean flames. There are other benefits of plasma-assisted combustion beyond NOx and soot reduction. There are issues with aircraft going off at high altitude. You need to relight them, and it's like a bathtub of cold kerosene that you need to ignite, and it's very difficult to do. You want to control regimes, transient regimes for a helicopter going up and down very quickly. There are instabilities that can damage engines that you can control, and so on and so forth. And so it's something really that has attracted the interest of the plasma community. So I will now move to part 2, which is plasma discharges, what kind of plasma discharge to use for plasma-assisted combustion. Then I will mention a few demonstrations of plasma-assisted combustion in real burners. And then we'll dive a little bit into the physics behind what the plasma does in terms of chemical, thermal, and hydrodynamic effects. Then we'll use this knowledge to develop models and to do simulations. And then I will return to the problem of NOx emissions, which is still a big issue. Okay, plasma discharges, there are many types. The question is which one to choose. Of course, there is a wide variety of electron densities, electron temperatures that you can create when you talk about plasma. And it turns out we were greatly helped in this endeavor by a program that took place in the US at Stanford when I was there. From 1997 to 2002, it was a program supported by the Air Force Office of Scientific Research. Basically what happened is this, Svetlana probably remembers it. There was an Ajax project that came out of Russia. And they had this concept of an aircraft, of a futuristic aircraft with lots of things. MHD propulsion, shock strength reduction, and so on and so forth. They also made it invisible to radar by cloaking it with a plasma. And when the Air Force, US Air Force, saw that, they got really scared. And so they called all the scientists to Colorado Springs in 1995, and they said, okay, you have to do something about it. We have to do the same thing. And so they said, okay, and one of the things we would like to do is to surround aircrafts with a plasma to protect it from electromagnetic waves. There was a problem, however. To do that, the Air Force realized the cubic meter of plasma, of air plasma, cost about 27 gigawatt of power, which is a little bit high. It's about the same power as the largest dam in the world in China, the Three Gorge Dam. And so the Air Force, not being afraid of anything, just said, okay, let's start a research program. You have 5 years to reduce this power necessary to make a plasma in air by a factor 1,000. And you know, it's like in football, competition is better if you want to achieve success. So they started the West Coast against an East Coast consortium, and I had the chance to lead the West Coast consortium with Stanford and Minnesota and Boeing. And the result was that we managed to reduce by a factor of about 1,000, actually, the power needed. And we did that using a new type of plasma, which is produced with nanosecond repetitive pulses, which are called NRP. So the principle is to use short, high voltage pulses. When I say short, it's only 10 nanoseconds, you see, in width, a few kilovolts. These types of pulses had been known for a long time to be useful for ignition. But the difference in what we did here was to apply them at high repetition frequencies. And this is a totally different type of plasma, because what you have is electrons that are produced during each pulse, and then they decay, and they don't go down to zero, so when you reignite, it's quite easy. And so you can maintain a fairly high electron density with a very low power budget, because the duty cycle is very, very small. The on time of the pulse is very short compared to the off time. Here is a picture of a typical plasma generated by these NRP discharges in air. And of course, it's good from the perspective of the power budget. So this has opened up a lot of applications, and now these plasmas are used around the world. So I'm going to show you now how we use them in various applications to stabilize what I mentioned earlier, lean flames. Here is a first experiment which was done at the M2C lab a while ago, actually. It's a methane air or propane air flame, 11 kilowatt, not so high power. Basically, we have here a flow, and we place what's called a bluff body. It's something, it's an obstacle that makes sure that the flow recirculates and spends enough time between the two electrodes to stabilize the flame. And here is a picture on the right. The plasma is here. And so then I will show you my favorite movie, which is a plasma stabilized flame. So we have here the mini-pack burner. Whoops. We will start with a stoichiometric flame, and we will reduce the fuel equivalence ratio. You will see that initially when phi is equal to 1, the flame is very stable, and then you will see what happens. So the flame is 11 kilowatts. So we increase the amount of air. The flow rate of propane is constant, so the power is constant. There is no plasma, but the flame becomes very unstable when it gets very near. And when it's near extinction, we apply plasma. You're going to see it now. Okay. And you can see that we recover a very stable flame. Again, this is without plasma and with plasma. But we do that with very little power, only 75 watts, which is 0.6% of the power of the flame. So this is realistic. Imagine if it were 1,000 times more, we would spend more power creating the plasma than we would get from the flame. That's why the power budget was very important. Okay, and well, with this burner, this is what we obtain in terms of extension of the stable limits towards the lean regime. Here is the fuel equivalence ratio as a function of the airflow rate. Above the black line, you have a stable flame without plasma. Below, it's unstable. Well, with the plasma, you lower this limit by about 10%. And you do that with a very low plasma power. Here is another example. Now, I'm going to show you several examples on laboratory scale burners. This one, and I will change some conditions. This one is a 52 kilowatts, so higher power. Before it was 11. It's still propane air, 1 bar, still atmospheric pressure. Now what's changed, it's no longer a bluff body injector, it's a swirled injector. These are types of injectors that are used in industry, and the swirled injector is more used for aircraft engines. So it's, you can see the size, you are starting to have large powers. The way it works, it's called a multi-point burner because there are 2 stages. Here is a first stage injection which, where you create a small pilot flame that will keep the flame alive. And then you have the main injection that comes through a secondary stage. And overall, the flame is lean. But the pilot tends to be rich. And basically, if you compare what happens without and with the plasma, without the plasma, the flame extinguishes for phi equals 0.4, whereas with the plasma, you can go down to much lower fuel equivalence ratio, much leaner flames. So you gain a factor of 4 in the lean extinction limit. So that was very encouraging as well. Then we went to flames in collaboration with Onera. Higher power. Well, this burner can go to 200 kilowatt, but we stopped at 53 kilowatt. Now, the difference with before is that we use a real fuel, kerosene. And it's also at slightly higher pressure, closer to applications. And again, in this case, we're able to decrease the extinction limit by a factor of 2, and with, again, very little power consumed. Another case was recently done at EM2C, and this was this time with a liquid fuel, N-heptane and dodecane. So here is the chamber. It's a swirled injector that produces this type of swirling flame. It's inside the cavity, the quartz cavity. And basically, we put the plasma here in a region where the flow recirculates and spends some time. N-heptane and dodecane are liquid fuels that are sprayed here at the bottom of the burner. And again, the game is to extend the lean extinction limit. And without plasma, well, the flame, this is a nice flame, this is what you want. But when you decrease the fuel equivalence ratio, at some point, the flame starts oscillating between they call it a tulip-shaped flame and an M-shaped flame. And it starts beating, and you know it's a bad sign, because soon after it extinguishes. So now what happens with the plasma? Well, with the plasma, you can keep burning down to a much lower regime of fire. And again, 1%, less than 1% of the flame power. Okay, and this is a summary. Basically, I don't want you to read all this table, but these are all the experiments I'm aware of that have been done on flame stabilization with plasmas. And you have here basically different burner types, bluff body, swirled. I talked to you about them, but also this is something done at NASA. It's a lean direct injection for the experts here in combustion. So it seems to work in all these cases. It works with all these fuels, methane, propane, kerosene, heptane, dodecane, natural gas. Pressures, it seems to work at higher pressures. People have worked until 5 bar. Flame powers, pretty much up to, to decent flame powers, 50 kilowatt. But still, we are far from an aircraft engine, which is at about 10 megawatt. So there is a need for scaling up. And what's interesting is every time we used less than 1% of the power of the flame to produce the plasma. So, okay, so these discharges work pretty well in many types of fuels, gas or liquids. Okay, now the question is why, and why? What do they do? What happens when you apply plasma? Well, here we need to go a little bit into details about the physics, and we will try to explain 3 types of effects: chemical effects, thermal effects, and hydrodynamic effects. And then in the next part, we will use this knowledge to simulate, see if we can simulate plasma-assisted combustion. So the first thing to determine is when you apply an electric field between 2 electrodes, you know that the field will accelerate electrons, and these electrons at high velocity will go and do things to the gas. What will they do? Well, you can calculate it, and so this is where the power of the electron goes. The fraction of this is the fraction of power lost by the electrons as a function of something which is called the reduced electric field. It's basically the electric field divided by the density of the gas, and this unit, strange unit, is called a Townsend. Okay, and basically what you see is that at low reduced electric field, the plasma makes molecules in air, this is in air, makes molecules vibrate and rotate, but not much more. And that doesn't do much for combustion. A rotating molecule, okay, it's a little bit hot, but that's it. If you go higher in electric field, from 10 to 100 Townsend, you see that you have the blue curve here. You mostly excite the vibrations of N2. And that also is not very efficient. for plasma-assisted combustion. It gets really interesting when you are above 100 tons N, because then you do the pink curve is ionization of the molecules, electronic excitation of O2 molecules, and electronic excitation of nitrogen. And we see that about 70% of the energy of the electrons, of the electric energy deposited, serves to excite nitrogen. Okay, when nitrogen can be excited to several states, and they are named, the ground state is called the X state, and then you have the A state, B state, C state, and so on. Okay, what can you do when you have these states? Well, here is N2, N2A, N2B. Here is another state, A prime. Here is the dissociation limit, and N2C. Well, if you look at it, all these states, even the first one, have more energy, have enough energy to dissociate O2, or CO2, H2O, CH4, or H2. And so in principle, assuming that there is no energy barrier to slow down the reaction, well, you can in principle dissociate all these species. And these are all the species you find especially in flames. In flames, you have O2 and 2, you have CH4, if it's a methane air flame, but you have also burned gases, which are CO2 and H2O. And so you can see that there is a lot of hope. Okay, then, well, we decided to look at what happened in pure air. Because in first order, a flame is pure air. The fraction of fuel is only a few percent, even in stoichiometric flames, except in hydrogen, where it's a bit higher. And so we spent a lot of time investigating what happened between two electrodes in air at 1,000 Kelvin, to be somewhat close to the conditions of a flame. And we tried to apply pulses, always the same amplitude, few kilovolts, 10 nanoseconds, at 10 kilohertz. And we looked at what happened here. We did time and space resolved measurements of species and temperatures. Okay. One of the things we wanted to know was what happens through the mechanism I mentioned, electrons exciting O2, producing N2 star, and then N2 star dissociating O2, producing two oxygen atoms, with the difference of energy going as heat. This mechanism had been proposed actually by Popov in 2001, but had not been proven for nanosecond discharges. It had been proven for microsecond discharges. Okay, so to do that, to validate this mechanism, you need to basically measure all the species, measure the temperature, measure the current, the voltage, the energy, and then of course, the difficulty is to do diagnostics with nanosecond resolution, 50 micron spatial resolution, and to synchronize the electrical measurements, the optical measurements. I think the main difficulty is nanosecond. So we developed several diagnostics. Here is a setup for cavity ring-down spectroscopy that we do in the lab. And this curve basically took us maybe 4 years to get and occupied maybe 2 postdocs and 2 PhD students. And Dave spent a lot of time on it. And what we have here is various measurements synchronized in time. The times, I want to insist on the time scale here. It's from 0 to 50 nanoseconds. So each point, the points are every few nanoseconds. And this is what happens in the discharge column. So here at the top, you have the voltage pulse, which is, you see, it's about 10 nanoseconds in duration. The current goes up to 300 amps. Then we have the temperature, the density of O atoms, and the 3 excited states of N2. Okay, from the curve at the top, if you do the product of voltage and current, you can get the energy if you integrate over time, and we can determine it from that. The second curve showed that the temperature increased from 1500 Kelvin to 2500 Kelvin in 20 nanoseconds. That's what's called ultra-fast heating. The oxygen density also increased quite a bit. In fact, it parallels the temperature increase. And it's remarkable to see that here you have this number density of oxygen atom corresponds to full dissociation of O2, which means that the discharge dissociated all the oxygen between the two electrodes, which was a very surprising result, right? Prior to that, people thought that, oh, okay, the plasma probably produces a few ppm of oxygen, of radicals, and there we see that it's massive production. So people didn't believe us for a long time, and so we spent a lot of time verifying that. And then finally, you see that the last curve, the electronic state density, here you have 2% of all nitrogen molecules, here at this point, in the B state, 2%. So it's quite a strong, efficient excitation. Okay, we deduced the fraction of energy, of the pulse energy going into gas heating, 20%. Here we had 50% dissociation of O2, so that was 35% of the pulse energy, so quite efficient, going into fast dissociation. And most importantly, you see that the increase of temperature, most of the increase of temperature in O occurs when N2B and N2C are decreasing. And so this confirms that we have this reaction at play, N2 star plus O2 producing oxygen plus heat. Okay, and moderate heating, less than 1,000 Kelvin. It's not like a big spark where the temperature can increase by 50,000 Kelvin. Okay, we compared this with numerical simulations done by Nikolai Popov, and basically he found that, yeah, the measurements were in agreement with his model. We also checked that what happened when you apply, if you heat the gas in such a short time, 10 nanoseconds by 1,000 Kelvin, then you should have shock waves. Well, we looked at that. We took this series with Schlieren imaging, and basically we had a pulse here, 2 electrodes, there is a flow, and it's repetitive, so you see a reminiscence from the previous pulses. And what you see after a few nanoseconds, you see a shock wave emerging here. Here you see it more clearly. After 5 microseconds, 10 microseconds, and then after 16 microseconds, it's gone. So we studied that, and also you hear a sound when you have sparks. They go tack, 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 tack. That made sense, but you can also see the sound, if I can say, from these experiments. So you have shock waves and a hot channel, and for a long time we thought that was the only thing happening. And then a student had the curiosity to look at longer times, go past 16 microseconds. Here you see that the column stays very cylindrical. And in fact, something surprising happens, especially when you have a very short gap. At long times, you have basically the discharge goes from a cylinder to a toroid. And we confirmed that with these experiments where we have a crosscut of the flow with the laser-induced fluorescence. Well, this was actually also very interesting because you see that initially the plasma produces species between the 2 electrodes here, but then it sends them into a very large volume, and so it can be very effective in stabilizing the flow. And so in summary, we, based on these results and also on numerical simulations, we were able to describe the effects of the nanosecond pulse here. Basically, you have ultra-fast dissociation of O2 in about 20 nanoseconds. Ultra-fast heating, that's moderate. Ultra-fast, slower heating, also moderate. This is at 100 microsecond time scales, and shock waves. Shock waves and the torsives. And furthermore, we were able to quantify the amount of the fraction of energy going into each of these modes. And these are the numbers I mentioned before. So this enabled us to develop a phenomenological model of nanosecond discharges that basically captures the main effects at 0th order of the pulse. And this, it's important to have such simplified models because otherwise there is no hope of developing, full-scale models of plasma-assisted engines. So to summarize, how do the plasma stabilize the flames? You have these electrodes. Electrons are accelerated. They excite molecules of N2 into various excited states, and then those dissociate O2, and the difference of energy goes into heat. You also have some dissociation, direct dissociation of O2, okay, but most of the process goes through this ultra-fast process here. In the end, you have oxygen atoms here and here. And these are good oxidizer of the fuel. So if you take a fuel molecule, RH, where R is a radical, CH3, for instance. So this CH4 plus O, you make OH, and then you start combustion. So the interesting thing about NRP discharge is they make lots of O atoms, and so they really boost the combustion. And the second effect is the heat increases the temperature of the gas, and this induces thermal and hydrodynamic effects. All right, and so these are the conclusions of this second part to tell you that we understand pretty well the effects of these discharges in air. We have refined this model to do the same for a mixture of burned gases and other things. But this should give us a good basis for modeling. And so this is the next to last part. It's going to be shorter, but I want to show you what we can do today with the models. We took basically the mini-pack burner. We took our NRP discharge model. We assumed that the plasma is a cylinder of diameter 500 microns. We use this simplified thing. Then we put that into this code, which is developed in Toulouse by Serfax. It's a combustion code. It's called A Very Big Project, AVBP. And we basically inserted our model here into the code. So there are no detailed plasma kinetics. They occur too quickly and are too complex to be simulated. So we have the simple plasma model. On the other hand, we have a detailed combustion model. We have large eddy simulations and turbulence, and so it's a fully three-dimensional model. And we were able to simulate the mini-pack burner. So I'm going to show you two simulations. The one on the left is with the nominal model, where we have these effects here, these fractions of electric energy dissipation. And then on the right, I will show you what happens if you don't consider the ultra-fast dissociation, which meaning that you have only kinetic effects, thermal effects. Okay. So on the left, we apply 10 pulses. We start from extinguished flame, and you have the 3D simulations here. You see the turbulence, and you see that the flame is growing nicely, is developing, and after 10 pulses are sufficient to ignite the flame and to get what we saw in the experiments. So ignition works. Now, if you were to put only the energy only into thermal effects, this is what happens. Basically, the discharge tries to start, but well, it doesn't go anywhere. And so you can even go on for 100 pulses, and basically nothing happens. So basically no ignition in that case. And so this is a clear proof that for these conditions, it's a kinetic effect. And this was something we had been wondering for a long time. Is it a thermal effect? Is it a kinetic effect? And so we're able to answer that question. Okay, can we validate this work experimentally? Well, we did that by doing measurements in the transient phase, going from a little flame, that was nearly extinguished, to a plasma stabilized flame. And so we did measurements at regular time intervals. Initially, you see there is no discharge, and here you have the discharge. So at time 0, we start applying the pulses. And we've done two things. We measured radicals, which was OH, because it's easy to measure. And we measured the temperature. And we will see how it evolves. So first, OH. So here is the bluff body, here is the electrode, and here is the laser beam. And we see the fluorescence from OH. Here are the measurements. So this is basically the edge of the bluff body here and here. And initially, when there is just the pilot flame, we have the measured profile of OH and the simulations. And okay, we get a correct shape. Then when we apply one pulse, this is what happens. Measurements and simulations. And then 2 pulses. And here, okay, well, the measurements are a bit narrower, but still we get a good idea of what's happening. And then at 45 microseconds, you see that you have the purple shape, and it's in pretty good agreement with the simulations. So this is a good validation of the chemical effects. Now, the thermal effects, well, again, starting from the first point to the stable flame, we measured the temperature here at the beginning of each pulse. Again, it's time resolved, and you can see that the measurements really match the envelope of the numerical simulations. So again, we have a good validation of the thermal effects, and it's actually nice because it's a very simple model. Very simple, but I should have said that these simulations that I showed you here took, with 100 pulses, they take 24 hours on 528 processors. So imagine with a detailed plasma model, you couldn't do that in 3D. Okay, and last, I want to finish with the NOx emissions, because that's where I started from. Well, this is where there is a lot of work left to do. There are very few experiments with NOx emissions. This is one that we did a while ago, where we measure the flame, the NOx emission as a function of the fuel equivalence ratio. So this is a flame without plasma, and you see that indeed the NOx emissions decrease when you decrease the fuel equivalence ratio, as expected. But then we did an experiment with 10 nanosecond pulses at 30 kilohertz. And here we saw that we didn't decrease so much the NOx, which means that the plasma produces NOx on its own. Fortunately, there are other cases where you see the plasma, this is the plasma at 10 kilohertz, it produces, the NOxes are reduced. So we know it's possible, but we don't know what are the best conditions. And so this is a big challenge. But here, you see that if you do it too quickly, you can make the problem worse, the NOx problem worse. How are the NOx produced? Well, in 2 ways. First, on the left, without plasma, you have the Zeldovich reactions. It's a thermal mechanism. It's N2O plus O giving NO plus N. And on the right, you have the mechanism with the plasma. And it's very similar to the Zeldovich reaction. We've called it the excited Zeldovich mechanism. It's this excited nitrogen that the electrons produced that will produce NO. The first one is temperature dependent. So, well, this is what we did. We decreased the gas temperature. We operated lean, and this should work. The second one, on the other hand, is electric field dependent. And there is a lot of work to optimize the electric field, the discharge geometry, so that we can maximize NOx while minimizing, maximize the radicals, such as oxygen, and minimizing the NOx. We've started doing some work on that, and we've done some modeling, and it's actually promising. In this graph, I've shown what happens in a normal flame as a function of the temperature. It's a lean flame. And basically here, as a function of the temperature of the flame, you have the various species produced. The main species is N2 in air. But here you have an H2O CO2. The interesting ones are the radicals, such as O. O is in black. And you see that there are not many radicals. That's what you want to enhance. And NO is in violet. And there's a little bit of NO. So you want to increase the black and reduce the purple. Well, this is what happens with the nanosecond discharge that we modeled. Well, you see that at the same flame temperature, 2000 K, you can greatly enhance the O and keep the NOx at about the same level. So these are the types of studies we've started, and they are very promising, we think. Okay, so, and this is done in the framework of a project called Green Blue, which is a project with the objective of minimizing NOx emissions for sustainable aviation fuels. And, well, basically we will work on methane because it's just the same as a sustainable aviation fuel for all practical purposes of research, and for hydrogen. And we want to study the NRPs in mixtures with these fuels. We want to measure some key reactions, and for this we use femtosecond diagnostics, and want to develop further models of plasma-assisted combustion, make numerical simulations, and then scale up to high-power flames. We think that 300 kilowatt is a nice power target. And then we can try them on the on-air facilities, hopefully, in the future to see if we can do better. So this is the roadmap. And in the interest of time, I think I will skip that part. But basically, experiments will be done on the small facility I showed you, and on the new multi-point beamer combustor, which goes up to 300 kilowatts. And hopefully we will get scaling directions for industry. Okay, so I think I've given you an extensive overview of this field, where we came from, where we are going to. I think it's generating a lot of interest in the world. And there are very interesting next steps. I also wanted to say that a lot of people have been collaborating with us over the years, and that when I made the list, I was surprised. But there are many people nationally, many students from our group, the permanent staff, of course, the people from the combustion group at EM2C, some former research engineers at EM2C. Some of them have gone on to permanent positions around the world. Also collaborators from ONERA, from various labs in France, and also international collaborators who have provided great help. So thank you for your attention, and I'll be happy to answer questions.
Thank you, Christophe. So the talk is open for questions, discussions, if you have some. Maybe.
It's okay. I think it's okay, thank you. Yeah. So thank you very much for this talk. It was very interesting, and I have two questions. One question on the very last last slide, conclusion, and in the presentation you are speaking about chemical, thermal, and hydrodynamic effect. And later, when you analyze it and compare surfax modeling and the results of your experiments, you are speaking about chemistry and temperature effect, but not hydrodynamic. Can you comment and are there further some interesting issues?
Yeah. It's just that the hydrodynamic comes after the thermal effects. So when I
did they model something? Because for example,
they did model.
You have two types of discharge. One is spark already, one is not spark, and I get that hydrodynamic effects and the influence of combustion can be dramatically different.
Yes. We did model the hydrodynamic effects, and you can see that in the Schlieren, in the comparison with the here. Okay. Here is, I went very quickly, but these are 3D simulations. These are numerical simulations. And when you have this here, it induces these toruses, which are the result of baroclinic instability. I can actually show you a few things about that, if you want. It must be, let's see if I can find it quicker. Yeah. Voilà. Ah non. Je vais arriver. Ça c'est dans les. Okay. Okay, yeah. Here. Okay, you have the plasma, and basically this is the plasma column. It's been heated up, and there is a gradient of density, and there is a gradient of pressure. And basically, so there is a gradient of density because the plasma heated up this region, okay? And the gradient of density is perpendicular to the surface. Then there is a gradient of pressure. And when you have a long discharge, the gradient of pressure is tilted from the gradient of density. And this will induce rotation, vorticity. It's called the baroclinic instability. And this will make these recirculation zones where you have flow coming from the outside and re-entering. And if the gap is longer, the effect will be less. And basically, these are calculations of the flow velocities. If you have a short gap, the discharge will transform into a torus. If you have a long gap, the discharge will just grow diffusively. So what I mean is the hydrodynamic effects are the consequence of the thermal effects. So when I say that we do put everything in chemistry and in thermal, the thermal includes the hydrodynamic.
But maybe to go further, can you imagine, and we go to the after, can you imagine that the geometry of the plasma could play a role?
Yes.
Not waiting for the thermodynamics inducing hydrodynamic effects, but imposing them by the geometry.
Yes, and actually that's what we are trying to use when I say that we want to tailor the discharge geometry. Okay. Because if you can induce the recirculation, you can bring fresh gas and so decrease the temperature. And so this is a major issue, but it's complicated.
And dramatically important for combustion, as far as I understand. My second question is about slide number 48. That's about fast gas, about your calculations. Oh, surfax calculations again. If you're speaking about fast gas heating.
45, you said? Here.
48. It's okay. If we're speaking about fast gas heating, no, it was 48 still, I'm sorry.
48. Where is it? Here.
Yes, right.
Okay.
When we're speaking about fast gas heating in principle, in not air, but air-fuel mixtures. I
Yeah.
do understand that we have like 2% of fuel.
Right.
That's correct. But still, can actually you say, looking at your calculations and even comparing O4H numbers, etc., that the fast gas heating in fuel-air mixture, to speak about hydrogen air mixtures, stoichiometrical S, is mainly the same as in air.
Yeah, that's...
And that you have experimental confirmation what is important.
Yeah. Well, okay, the first answer is these measurements are taken in a flame. And the model is done by assuming no effects on the fuel. So essentially, these results are surprisingly close. Well, there are some differences, you see, maybe between this green curve measured and the simulation. But they are not huge. So that's what I'm saying, this model to first order is amazing, because it's amazingly simple. You know, I mean, instead of having thousands and thousands of reactions, you just have 3 parameters, and boom, you can capture the basics of the physics. So, we came up with a new model now that takes into account the fuel molecules, and we hope to test it before June of next year.
Which is very interesting, because actually Popov just published a review, if you're the
I know.
journal about fast gas heating.
I know.
And we are really sorry, not to have this data.
And it's a very nice review that you published. We've used it too. But yeah, no, you're right. There's a lot of data missing, and we plan to measure some of the missing data.
Thank you.
Hopefully. But of course, you need to do it with. It's challenging because it's very short and very small.
Other question, maybe? No? Well, you started with the Ajax competition. Okay, 1 cubic meter, I don't know how.
27 gigawatts.
Okay, and the challenge was to reduce by a factor of 3 orders of magnitude. Yeah?
Right.
So you demonstrated something, I guess, from the kilowatt to the few tenths of watts.
Yeah,
so
right.
Is it scalable when?
That's a good question. The biggest pulsars that I know are probably what, maybe Svetlana, you know more, 10 kilowatt, perhaps? 10 kilowatts, so you could stabilize a 10 megawatt aircraft. Now, the idea is, it's like in combustion. If you have combustion chambers, they are annular with multiple, as you know very well, multiple injectors, and so the idea is to put them in parallel. So 10 megawatts, you can get to 100 megawatts. I think for aircraft, it becomes interesting, yeah. Also, our latest results show that we are closer to 0.1% of the power of the flame to stabilize. So I think there's hope, yeah.
Okay, last question.
You had mentioned that you want to manage this excited Zeldovich reaction. But at the same time, it involves the N2 star species that also create the O in the first place.
Right.
A lot of it. So would that involve something like manipulating the field?
Yeah. Yeah, essentially. And so
choosing just the right field such that...
yeah, the right field, the right pulsing pattern, and the geometry also. So,
the geometry.
Yeah.
So it wouldn't involve any kind of physical separation of the species or something like that?
Well, if you have ideas about how to do that, that'd be interesting. No, but it has to be removed. You don't have much time, and it's hot for filtering. So I don't know. Perhaps.
Actually, what I played with is mainly thermal dependence. Not this slide, but the slide where you showed a principal possibility.
I'm sorry.
About NOx. The last physical slide about NOx.
Yes.
So it's temperature dependence.
It's temperature dependent.
Excited Zeldovich mechanism and temperature dependence.
Right.
Which is actually absent of intrusive production.
Voilà.
Okay, thank you again. We will stop here. Thank you.
Thank you. Thank you. Thank you for coming.